Welcome to the Deep Dive. Ever wonder how scientists build those incredibly complex molecules, the ones in medicines, materials, all around us?
It's fascinating stuff.
Well, today we're cracking open the chemist's toolbox and zeroing in on one element you might not expect, sulfur.
That's right. We've been diving into Advances in Sulfur Chemistry, Volume 2. It's edited by Christopher M. Rayner.
Right.
And it's basically a masterclass in sulfur's, well, molecular magic. Covers a huge range: thioacylsilanes, chiral sulfoxides, lots of complex names, but really interesting chemistry.
Okay, so our mission here is to pull out the really compelling bits, how sulfur is used strategically to build these intricate molecules.
Exactly. Think of it as a shortcut to understanding some seriously ingenious chemistry.
All right, let's dive in then. Thioacylsilanes first. You describe them as shy molecules with a silicon bodyguard.
Yeah, something like that. Bianca Flavia Bonini and Maria Francesca Focci wrote this chapter. Basically, thioacylsilanes have a carbon-sulfur double bond, but it's right next to a silicon atom.
And that silicon makes all the difference.
It really does. It dramatically changes how that CS bond behaves, making these compounds super useful in synthesis.
Okay, so how do chemists actually make them? The book mentioned something about acylsilanes and hydrogen sulfide, acid catalyzed.
Yeah, that's one key method. Acylsilanes, H2S, HCl, but like you hinted, there's a catch.
What's that?
Well, the thioacylsilanes you get can be a bit sensitive to heat, thermally unstable.
Right, so handle with care. But that reactivity is also the point, isn't it?
Precisely. That's what makes them valuable. For instance, they react really nicely with organometallic reagents.
Like Grignard reagents.
Yes.
And organolithiums. The sort of things chemists use to snap carbon pieces together.
Exactly those. And you can get all sorts of useful products like acyl-vinyl sulfides.
Which are building blocks themselves, I guess.
Very handy ones.
Okay, but here's where I thought it got really clever. The cycloadditions.
Oh, yeah, definitely.
Like the 4+2 cycloadditions with diines. It's like molecular Lego, right?
Yeah.
Snapping pieces together to make rings.
Exactly. Sulfur-containing rings. And what's key is the control you get.
You mean where things attach and the 3D arrangement, that regio and stereoselectivity stuff?
Precisely. You get very specific outcomes, which is fantastic for synthesis.
But maybe the most strategic use is acting as stand-ins for those unstable thialdehydes.
Yes, that's a huge application. Thialdehydes themselves are, well, notoriously difficult to handle. Very reactive, fleeting.
So the thioacylsilane is like a masked version.
You got it. The silicon acts like a temporary cap, protecting that reactive group. You do your reaction, then you just remove the silicon.
And boom, you've delivered the thialdehyde exactly when and where you needed it.
Right. It's like having a stunt double for a really volatile molecule.
That's genius. They also mentioned using them as spin traps for detecting free radicals with ESR.
Just another example of their versatility. Like tiny molecular detectives, as you said.
Cool. Okay, so that's thioacylsilanes. Now, building on that theme of sulfur being versatile, let's talk about carbohydrates. Seems like a totally different area.
It is. But sulfur plays a key role there, too, particularly with iodine.
Yes, iodine. Good old first aid kit staple. But K.P. Ravindranath Kartha and his colleagues show it's way more than that, right? It's like a master architect for building sugars.
That's a great way to put it. It's vital in glycosylation reactions. That's how you link sugar units together to build complex carbohydrates.
Who knew? So how does it work? The chapter talks about iodine activating thioglycosides.
Yeah, thioglycosides are sugars linked through sulfur. Iodine acts as a promoter, basically giving them the nudge they need to connect and form those crucial glycosidic bonds.
It provides the activation energy, sort of.
Sort of, yeah. It facilitates the reaction.
And it's not just the easy ones. They mentioned disarmed thioglycosides, the less reactive ones.
Right. Those can be a real headache with other methods, but iodine-based reagents can often activate them effectively. It's a powerful tool.
Are there downsides, though? Like, could the iodine cause unwanted side reactions sometimes?
That's always a consideration, yeah. You have to control the conditions carefully. But iodine offers multiple activation modes. It can also act as a Lewis acid.
Oh, okay. So it can activate glycosyl sulfoxides too, not just the thioglycosides.
Exactly. It gives chemists different pathways depending on the specific building blocks they're using.
So it's like having different keys for different locks when connecting sugars. And you can fine-tune things, too, by pairing iodine with other stuff.
Different promoters, different leaving groups. It gives you a lot of control over the reactivity.
Which sounds super important for building complex carbohydrates precisely.
It really is. And remember, these carbohydrates are involved in, well, almost everything biological. Cell signaling, energy, disease recognition.
Right. So advances here directly impact medicine and biotech.
Absolutely. Developing better ways to make these molecules is crucial.
Okay. So from sugars, let's shift again. Chiral sulfoxides, sulfur deciding which mirror image molecule gets made.
Precisely. Nuruddin Kiar and his co-authors cover this. Sulfoxides, have sulfur bonded to oxygen and 2 carbons.
And that sulfur can be chiral, like left and right hand.
Exactly, a chiral center. So you get these non-superimposable mirror images and enantiomers, and making just one of those is often critical, especially in pharmaceuticals.
That's asymmetric synthesis, right?
Yeah.
And these chiral sulfoxides are building blocks or auxiliaries, temporary guides.
Both. They can be part of the final molecule, or they can be used temporarily to control the stereochemistry of a reaction and then removed. That's a chiral auxiliary.
But getting mostly one mirror image, a high E, and antiomeric excess, that's the hard part, I bet.
Oh, yeah. That's the challenge. The chapter dives into some really ingenious ways chemists tackle this, mostly through asymmetric oxidation of sulfides.
Okay, like what? They mentioned chiral auxiliaries again, attaching something chiral temporarily.
You attach a chiral piece to the sulfide, do the oxidation, and the auxiliary kind of steers the reaction to make one sulfoxide enantiomer preferentially. Then you take the auxiliary off.
Clever. What else? Chiral catalysts.
Right. Things like titanium tartrate complexes, reminiscent of the sharpless epoxidation, which won a Nobel Prize for its control.
Wow. So the catalyst itself is chiral and promotes one outcome.
Exactly. And it's not just chemicals, biocatalysis too, using enzymes or even whole microorganisms.
And nature's catalysts.
Yeah.
Are there challenges with those, though? Like, are the enzymes always stable or specific enough?
That's a very good point. Enzyme stability, substrate scope, those can definitely be practical hurdles, but it's a growing field.
Okay. And the chapter also highlights the Orsay system. From Kagan's group. What's special there?
The Orsay system uses specific chiral titanium complexes. It's known for giving really, really high enantioselectivities for certain types of sulfoxidations. The chapter details the conditions.
High E's. Got it. And then there's the DAG methodology, using sugar derivatives, diacetone D-glucose.
Yeah, DAG stands for diacetone D-glucose. It's using derivatives of this readily available natural sugar as the chiral auxiliary.
Taking advantage of nature's chirality again.
Exactly. The chapter explains how it works, the mechanism, what factors influence the outcome. It's a really nice example of creative problem solving in synthesis.
Okay, cool. Now, sticking with chiral auxiliaries, but making them cyclic. Chapter by Allen and Bullman-Page. How does putting the sulfoxide in a ring change the game?
Right. So instead of the sulfoxide just hanging off the molecule, it's part of a ring structure. Think 1,3-dithiene 1-oxide, a 6-membered ring.
Okay.
That cyclic structure makes things more rigid, more defined geometrically. This often translates to even better control over subsequent reactions.
A more predictable environment, maybe.
Exactly. The chapter really focuses on those 6-membered rings. They talk about how to make them and, crucially, how that chiral sulfoxide within the ring influences reactions happening next door.
At the alpha carbons.
The sulfoxide basically creates a chiral nudge, forcing incoming reagents to approach from one specific direction.
So if you form a carbanion next to it and react it, say alkylation or allyl reactions.
Or conjugate additions, yeah. The chiral sulfoxide dictates the stereochemistry of the new bond being formed, often with really high diastereoselectivity.
Could you give a simple picture? Like, does it just physically block one side?
That's often the basic idea, yeah. Steric hindrance. Imagine the sulfoxide group and its substituents creating a bulky, asymmetric shape. The incoming molecule finds it much easier to approach from the less hindered side.
Makes sense. And they have specific examples showing this.
Oh, yes. Lots of examples illustrating the control. They also briefly mention 5-membered rings like 1,0,3-dithiolane 1-oxides. Similar concept, but sometimes with slightly different applications or reactivity.
It's amazing how these structural tweaks make such a difference. Okay, let's shift again. Unvious Carolina unsaturated sulfoxides and sulfones. Sounds like even more going on in these molecules.
They definitely have multiple reactive sites. Ian Forrestal and Christopher Rayner cover these. You've got a carbon-carbon double bond, an alkene conjugated with the sulfoxide or sulfone group.
So alkene reactivity plus sulfur reactivity.
Pretty much. That combination makes them incredibly versatile intermediates.
What kinds of reactions do they like to do?
Well, they're great Michael acceptors. That double bond is electron deficient because of the sulfur group, so nucleophiles love to attack the bar carbon.
Conjugate addition.
Right. And the sulfur group can influence both where the nucleophile adds the regioselectivity and the 3D outcome, the stereochemistry.
So, again, sulfur controlling the architecture. Useful for building up complex carbon skeletons, precisely.
Absolutely. And they're also great partners in cycloaddition reactions.
Like Diels-Alder again, using these as the dienophile.
Exactly. Or even as heterodinophiles. It's a powerful way to build rings with defined stereochemistry, often in just one step. The sulfur often plays a key role in controlling that 3D outcome.
And rearrangements, too. The Pummer rearrangement came up again.
It did. This chapter looks at Pummerer-type rearrangements, specifically involving these unsaturated systems. It shows how sulfur can mediate these, sometimes quite complex, shuffles of atoms to create new structures and functional groups.
Okay, let's stick with that Pummerer rearrangement for a moment. The next chapter, by Matsugi, Shibata, and Kita, is all about the asymmetric version. How do you control the stereochemistry of a rearrangement? Seems tricky.
It can be. So the basic Pummerer converts a sulfoxide to an unfunctionalized sulfide, right? To make it asymmetric, you need a source of chirality. Either you start with a chiral sulfoxide.
Okay, the chirality is built in.
Or you use a chiral catalyst, often a chiral Lewis acid, to guide the rearrangement preferentially towards one enantiomeric product.
And this actually works. They get decent control.
Yes, the chapter shows examples where they achieve good enantiomeric or diastereomeric excesses. It often depends heavily on the specific molecule and the conditions, of course. Are there specific catalysts that work particularly well?
The chapter delves into some examples, yes, often involving chiral metal complexes, and they also touch on related rearrangements, sort of inspired by the Pummerer, broadening the scope of these sulfur-mediated transformations.
It really paints sulfur as this tiny molecular conductor orchestrating these precise changes.
Okay, next up, sulfonimins. Another sulfur-nitrogen compound. Sulfonimins, or N-sulfonimins, Pingzhu, Bangxi Chen, and Franklin Davis cover these. They've got a sulfur-nitrogen double bond, and crucially, the sulfur atom is often a chiral center.
Making them useful as chiral auxiliaries again, or intermediates.
Both, really. That stereogenic sulfur combined with the imosmin functionality makes them very versatile.
How are they typically made?
Usually by reacting sulfoxides with imosmins or similar nitrogen sources. The goal is to form that S-N bond while keeping or creating the chirality you want at the sulfur.
And what makes them so useful in synthesis? What reactions do they do?
Well, they act as electrophiles. That Emma's carbon is susceptible to attack by nucleophiles, think Grignards, enolates again.
Okay.
And here's the key part. Because the sulfonamin itself is chiral at sulfur, the addition of the nucleophile often happens with high diastereoselectivity.
Meaning the new chiral center you form has a specific relationship to the sulfur's chirality. Exactly. The sulfonamine acts as a chiral template, guiding the formation of new stereocenters.
That's powerful for building complexity. And they also work just as removable chiral auxiliaries.
Absolutely. Attach a chiral sulfonamine, do your reaction elsewhere on the molecule where the sulfonamine's chirality directs the outcome, then cleave off the sulfonamine.
Leaving behind your enantiomerically enriched product.
Precisely. Sulfur as the temporary chiral director again.
It's a recurring theme. Okay, finally, sulfoxamines. Covered by Stephen Pine in quite a long chapter, suggesting they're pretty important.
They really are. Sulfoxamines are closely related to sulfonamines, but they have both a sulfur-oxygen double bond and a sulfur-nitrogen bond, often with the nitrogen substituted.
So S-O-N and 2 carbons around the sulfur.
Essentially, yes. That structure makes them even more versatile than sulfonamines, often more stable and easier to handle too, which is a big plus in the lab.
Easier to work with. Always good. How do chemists get them in an enantiomerically pure form?
Similar strategies as for chiral sulfoxides, asymmetric synthesis routes, or resolution of racemic mixtures.
Okay. And their applications seem really broad.
Incredibly broad. Chiral sulfoxamines are used to control stereochemistry in a huge range of reactions. Alkylation of enolates, aldol reactions, conjugate additions, cycloadditions, you name it.
And they give good results. high selectivity.
Often exceptionally high diastereoselectivity. They're real workhorses for controlling stereochemistry in complex settings.
Like supercharged chiral controllers.
Yeah.
And they can be used as auxiliaries too, like the sulfonimins. Attach, direct, remove.
Exactly the same principle. Attach the sulfoxamine auxiliary, let its chirality control a reaction somewhere else, then cleave it off to get your enantiomerically enriched product. It's a widely used strategy.
And it sounds like this has real-world impact, used in making complex natural products or drugs.
Yes, the chapter gives examples of their use in total synthesis. Building these incredibly intricate molecules often relies heavily on methods like these that offer such precise stereochemical control.
Wow, what an incredible journey through sulfur chemistry. It's way more than just smelly compounds, isn't it?
Oh, absolutely. These sulfur compounds are sophisticated, highly versatile tools for chemists.
Yeah, the sheer range of things they can do, highlighted across all these chapters. It's remarkable.
From acting as temporary masks or protecting groups, to actively directing the 3D shape of molecules with amazing precision, sulfur is critical in modern synthesis.
The thing that really stuck with me is that idea of sulfur as a temporary handle. Allowing chemists to manipulate shape and reactivity, and then maybe removing it later, like tiny removable molecular architects.
That's a perfect analogy. And its ability to mediate those complex rearrangements, like the pomerer, or help form those vital glycosidic bonds, it really highlights its unique chemical personality.
And for you listening, while this sounds super specialized, unsaturated sulfones and all that, it's important to remember this is the foundational work that leads to new medicines, materials, all sorts of technologies that really do impact our lives.
Absolutely. This kind of fundamental chemistry enables so much innovation downstream.
Which kind of leaves you wondering, doesn't it? If we can harness a relatively simple element like sulfur in such sophisticated ways.
Yeah. What else is out there?
Right. What other fundamental building blocks of nature might hold similar untapped potential, just waiting for chemists to figure out how to use them as tools?
It's a fascinating thought. What other molecular magic is waiting to be discovered? Makes you really think about the future possibilities in chemistry.